To process the video data, we first get access to the raw pixels. To do this, we allocate a new buffer. It's called image buffer. Convert the video sample to an image buffer. In this way, we can access the data in the form of an image. Then notice this pair of lock and unlock instructions. That means during our access to the data, please lock the buffer without letting anybody to change its content. So now let us to get access to format the data into an image. For an image, we need 4 pieces of information: the dimension of the image, which means the height and the width of the image, and the size of each pixel, which we call, in our terminology, it is stride, which means to have a pointer in the memory, point to one pixel, move to the next one, how many bytes you need to jump. It's called a stride. And of course, the address of the image data itself. Let us put all this information in a data structure. We call it a frame. We can declare the frame here. As usual, I just put everything in our view controller. But in real applications, you probably want to put such basic type declaration in some header files that can be easily shared in all the modules in your project. We type div, and we need a struct. We call struct blue, green, red, alpha frame. For this frame, need its width, height, stride, and the pointer to the data. Pointer, we use the basic pointer, which is a byte. Usually we represent it using unsigned character data. Actually, this data is not pointed to any characters. We just use this type name for 8-bit byte. Okay, let's go back to our we can declare a VGRA frame here. Then VGRA frame dot width equals CV pixel buffer get width, and the buffer would be our image buffer. GRA frame height CV pixel buffer get height, image buffer GRA frame stride CV pixel. Bytes per row. Oh, I made a small mistake. The stride actually point the pointer from one row to the next, instead of point it from one pixel to the next. Okay, image buffer. Now let's get the buffer itself, frame, the data itself, data pix, get base address, image buffer, fine. And we want to use type conversion, so that suits our needs. Please notice I have added 2 OpenGL instructions to prepare for drawing images. So let us display whatever we get from this image buffer to the display window we have allocated, we have prepared. The way to do that is we use some C core image object. It's called CI image. So image to create a CI image with CV image buffer. It is our image buffer. Okay. If we got this image right, if we get it, we can join it on the in the window. Before we join it, remember we need another context which is built upon the EAGL context, and that context we use that image context to show this source image. Let us build the context here. What we need is to add a property called CI core image context in this context, and in the setup context function, we prepare the context using create a context using context with EAGL context, and using the setup EAGL context get this core image context. Okay. Now we can display. So CI context display image, draw image. Yes, this is a signature we need. Source image. Preview view. This is the bound we have chosen for our view, and from this practice dot extend. Okay, let's try. Good. On my iPhone, it displays the camera image. Okay, we got the camera image and have shown it on screen. Good. Finally, we are ready to do some cool stuff about the image. Now we have the image read, and after doing something, we will be able to display the results. If you think about it, the image or video processing task, the really challenging part is to understand the contents in the image or the video, because after you have a good understanding of the scene or the object or a human face in front of you, you will be able to do some editing or rendering, drawing, stuff like that, using pretty standard methods. For the understanding part, there are a couple of good libraries and established methodologies for you to do that. What I will use today is a very good library. Actually, it is a de facto standard called open source computer vision library, OpenCV. The version, if you downloaded today's version, you got is OpenCV 3.2, but it has a pre-built framework for the development of iOS apps. For some unknown reasons, the framework of OpenCV 3.2 has a funny name called OpenCV 2.framework. I will provide a link on the UTS Online. I have got my framework downloaded, and next step is to put the framework in our project. Let's show our project in Finder. Click here and copy and paste my OpenCV2 framework here. Click the project setting and click this build phrases. If you remember, I mentioned that previously. I previously mentioned we need some framework to link with. These three are standard frameworks, come with the iOS SDK, and now we need to add our OpenCV. This is OpenCV framework. Open. Right. You will see that OpenCV2 framework appear in the framework subfolder in the project browser. Right. Let's try. This is an MM. Import OpenCV2 OpenCV HPP. Let us see how it works. The build was successful. Now we are able to use OpenCV library. Let us create a process frame processor. First example. It accepts a BGRE frame. We use a reference to a BGRE frame as the input-output argument for the frame processor. In the delegate, we call this processor before we release the image buffer. We can do this. Process frame. This is BGRE frame. Now the processor got such a frame, and in the frame it has all the information it's needed for an image. Note now, as we have the pointer to the internal memory of the image data, in this frame processor we are able to not only to access what is the data collected for the output symbol buffer, we can also adjust it. And later we will show this modified image using the OpenGL preview view. So the first task is to represent the frame image. using using an OpenCV format matrix. This is just a wrapper. Mat, we call it CV free. Okay, and let us give the mat some free dot height free dot width. The format is .cv8, that is the 8-bit unit. U means it is unsigned value, which means the value is from 0 to 255 instead from minus 128 to plus 127. C for channel, there are 4 channels in each pixel, just B, G, R, A. And the third parameter is actually where is the data, frame.data, and frame.stride to assist OpenCV to traverse or scan the data. We put some text, right? The input and output array means if we give an OpenCV matrix in this parameter, and the put text function will modify this the content of this matrix, and actually the value in this matrix will be changed. Sometimes function will get an input array and an output array. In that case, the matrix you pass in the input array won't get changed. That is guaranteed, and the output array will be modified. Okay, this can give it CV free. C, for example, power by OpenCV, and give it some point to show the message. Point 2i means a two-dimensional point coordinate in OpenCV format, and the x coordinate let it to be 10 and the y coordinate let it to be 20, and I means integer. Font face, give it some CV font. I find this type is pretty to see on screen, and the scale let it to be 1.0, and the color you can choose one color of your choice, but to remember that now we are dealing with 4 channel images. In this color we need to put transparent value in that. Just give it to 55. Okay, CV scalar. Note the name. The scalar means this value is applied per pixel. It does not mean that value has only one scalar value. Actually, we have 4 channels per pixel here. So let's use green. 0 to 55, 0 to 55. Okay. We have a warning here. Let's have a look. Okay, because the height and the width are in unsigned long integer, and here OpenCV wants integer value. We give it to some type conversion to eliminate this warning here. Have a try. The next step, I will demonstrate an example application in which I will let the algorithm to detect the circle shapes in the camera image. If there are multiple circles detected, I will show the detection by drawing the detected circles on the camera image. If there is only one circle detected, I will use that circle as an example of image processing. I will extract the content within the circle area and clean all the other part of the image to give a clean background and put the content within the circle in the clean background. It is like an application, for example, to extract customer signature from a document. The first step, let us make a copy of our frame because we want the for one thing is we may want to do manipulation steps on some copied buffer instead of the original buffer, and secondly, the circle detection method works only on grid level images. It does not work for the BGRA format. So let's connect grid frame. There is a very convenient function to convert image formats. Use CV convert color. Right. Now we notice there is input array and output array. In the input array, we give the CV frame here, and now it's guaranteed the value in the CV frame won't get changed. And the output array called, we use the grid frame here. The code instructs how to convert. It is CVBGRA to grid. Now we have a grid level frame. Next step is actually image processing. The actual image processing code. Processing the grid image to detect circles. If multiple font show them. If a single font extract content within the circle and clean background. Okay. Before we pass the grid level image to the detector, let us blur the image a little bit. We can eliminate some noises and to make the result more stable. Do some parameter setting first. We will need float detector blur scale. Okay. Now we use CV median blur, which change the value of a pixel to the median value of a neighborhood. The input image now is a grid frame, and the output image is also the grid frame. We use grid frame for input and output, which means the operation is in place. This way we can save some memory. The scale is detector blur scale. Let's do B5. Then we are ready to have the detector detect circles for us. First, let us allocate the storage for the detection result. See, we get a vector, and in this vector container, this vector is used. This standard vector is used a container, and to is not to be confused with the OpenCV vector here. OpenCV vector means actual mathematical object of a vector, which we used here is three-dimensional vector, and the element is of fluid type. That we call it circles. And in each of the vector 3 fluids, the first two fluids means the x and y coordinate of the circle, and the third one is the radius of the circle. Okay. Now we are ready to call our detector. It's called CV half circles. Okay. This is our input. Image is grid free, and the output circles is circles. There are a few parameters we can choose. Actually, this function signature is a simplified version. We have more controls of these half circles. Let me explain it. The first is detector resolution. Put it here. Which means to which resolution we want our detectors to run on. The larger the value, the finer the detector, because the detector will try to enlarge the image and find circles in the enlarged image. Sometimes you can find a circle's center at some sub-pixel position, but we do not want this behavior now. We use a resolution of 1.0, which means the detector will be running at the same resolution as the input image. The second parameter is mean dist. Let it to be 100. Okay, that means if multiple circles are detected on an image, because when the image has some noise, or the boundary of the circle is not crystal clear, which is normally the case in practical images. There are multiple choices for the center and the radius of the circle. In this case, it may not be a good idea to return all those possibilities. For each possible detection, we would want the detector return us only a single set of the center and the radius. This parameter here instruct the detector that to return me an independent detect, the minimum distance of a new detection to existing detection needs to be 100 pixels. So it will eliminate the possibility of many largely overlapping circles. It's called detector parameter 1. But its meaning is gradient threshold. The detector will run a contrast detection, a contrast computation over all images. Only when the contrast exists, the detector will consider the contrast is a possible edge of the circle. The larger, this is threshold. The larger is that, the less sensitive the detector will be, and the more difficult for a pattern to be recognized as a circle. Okay, I choose 100, which is normally a reasonable value here. The second one is called parameter 2, which is not very informative either. called accumulate threshold. This threshold means for a circle to be detected, how many high contrast positions on the circle need to be found so that the circle will be returned. For example, if a circle is only partially observed or only partially existing, you may find some arc pattern, and in the arc pattern you find some high contrast areas. But along the arc, you can calculate an imaginary circle. But how large the arc must be for the circle to be counted as a circle is controlled by this parameter. And 60 is generally you'd have to set such parameters by trial and error. We want some filtering in the detector, like to instruct the detector to ignore too small or too large circles, which is useful in practical applications. Maybe here. Okay, let's pass those parameters to our detector. The order for them is detect. Oh, sorry. Parameter 1, detect, parameter 2, and then detect mean. Figures. Max figures. After the solution, there is detect mean test. Okay. Then we perform our workflow. We check the number of circles has been detected. If the number is exactly 1, we do some processing. Otherwise, we try to show whatever detection is. Check if how many circles we have detected. If we detect 1 circle, we do some processing. Otherwise, we show the detections. Put the text here and show that, and also give out a message that the processing taken like token image taken. Okay. To draw all those detections, we need a for loop. Let I 0 I in circle the size. No. Circles I. Notice that now we use an integer vector. We convert the float vector into an integer vector for the purpose of drawing a circle on the image. There is a drawing function called CV circle, CV, no, CV free, and point C0, C1. The readers is C2, and we can use some color. Remember that scalar means per pixel, which is the full element, so-called scalar that we want to use BGR red, and A is 205. Okay, let the line width, how thick the line needs to be 3. Okay. Then let us draw the radius of the circle as well. It's a very small radius, so show actually where the radius is. Okay. Give it a green color. We got an error because we missed an argument to the circle detector, and it misinterpreted the next argument as the argument that was supposed to be there. Let us correct this error first. Missed argument for the detector, which means we use half gradient method. Okay. Do it again. Well, despite some instability and noises, it works. Now we have a circle detector. Next, we deal with the case of a single circle has been detected. We would like to take the image content within the circle and put this content in a clean image. The processing steps is the first two. Have a mask of the inner area of the circle, and then copy the input image content within the mask to a clean image. Of course, we would have to set up a clean image first. Okay. For the mask, we allocate a mask image. Mask image. That would be our grid frames size of the same size as the grid image, and the type, because it's a mask, it's only yes or no information for each pixel, whether to take this pixel from the input image to the clean image. So we give it 8 bits per pixel. Unsigned channel number is 1, and we initialize the mask with value 0. Secondly, we draw a circle in the detected circle. We draw a circle on the mask image and have it a CV point. Okay. Of course, let us find out the circle CV VEC3IC equals circles 0. Now we can copy this part to the joining function. Okay. And the value to draw scalar white. Okay. we want the mask to be the inner area, which means it should be filled. This is a pattern. Sure. Because we want the inner area, perhaps we want the radius slightly smaller than the detected circle's radius. Okay, this is what we use for the mask image. Actually, we can show the mask. We can check if we have the mask set up correctly or not. To do this, let us first convert the mask image as the same format as our CV frame. CV grid to VGRA and CV copy to okay mask image dot copy to over CV frame. Okay, let's check. Okay, let's try. Now I have a circle with a height in it. Say if, well, the circle is detected, although it is not very stable, but in most cases, this detected and the mask, if you can see in this way, the mask pretty much covered the content of the image. Okay, to see if there is more than one circle present in the image, what the program, what the app will behave. Let me put another circle here. Look, when it detects two circles, it will present the circle on screen instead of taking the mask. But well, the behavior is not very stable. Now it circulates from detecting one circle here, another circle here, and both of them. Okay, but you get the idea. Now our mask is working, and the next step, we want to create a clean image. In the same way we creating the mask image, we get a clean image. Let us call it token. Using the same size of the grid image and the grid scale format, but only this time we want an all or white image as the clean image. Next, we want copy the content from the grid frame, copy to the token image. We provide a secondary parameter to this copy to function, which is the mask. Only when the mask image has the value other than 0, the pixel value will be copied from the grid frame to the token image. Okay, this step we have done, and now let's perform some thresholding. That is to eliminate all the unwanted pixels as background and keep only the content we want. Let's check how it behaves, and let's the threshold to be 128 degree level, and the maximum value and the type. There are several types OpenCV can perform thresholding for you, like when the pixel value below the threshold, it put it to 0, and when it's above the threshold, put to the maximum value, which is 2055 here, or when it is below to the threshold, it do nothing, and above the threshold, it put to 2005. Such kind of operations. But now we want it to be a very simple thresholding. When it's below to the threshold, which is 128, it will put the pixel in as a value, put the 0 to the pixel, and when it is above the threshold, it will put the maximum value 255 to the pixel. This operation is called CV thresh. You see there's a set of different thresholding behavior here. We use the thresh binary. Finally, we change here from, we will output the token image. And replace the CV frame using the token image here. Right. Okay, let's see what we will get. Check detection working, and for the single image, a single circle, yes, it works. Like it takes the text within the circle and give us a clean image. Actually, I can, using my pencil to draw some. See, if I occlude most of the circle, it won't detect and it show me the image. If I show it the circle, it will detect the circle and extract the inner content. See what my pencil would look like inside the circle. Well, good. And let's give this stroke. Yeah, and this stroke. Okay, have my signature. That's this thresholding. If you draw it lightly, it won't be shown. If you make a strong stroke, it will be thresholding to the extreme value. Okay.